G'day, everyone. I know I have the difficult job of keeping you all entertained just before lunch when your minds are on the food. So let's get started in talking about how to analyze petabytes of data with serverless functions. So my agenda today is very simple. I'm going to tell you 4 things. First of all, how you can, how ideally you would be able to analyze petabytes of data using Lambda or Google Cloud Functions. Secondly, we'll talk about how things don't exactly live up to the advertisement and how things can be a little bit painful and how you can work around those problems. Third, we'll talk about how to look at problems and evaluate them and to see whether or not they're suitable for use with serverless. And then finally, we'll talk about a thing that I'm really passionate about, which is how to improve the environmental sustainability and the cost of your serverless workloads using ARM64. So first of all, let's talk about what Lambda or your favorite cloud provider's serverless functions are useful for. But I think that I want to use a concrete use case rather than just generically waxing poetic about oh, you could have a game shop or you could have a discount service, or no. Let's talk specifically about a use case, and that's my company's use case, Honeycombs. So Honeycomb encountered a problem about 5-6 years ago where we needed to optimize our custom data store, and the existing method of using regular physical servers was too slow for us. But what exactly is our custom data store for, you might ask? Well, it's a distributed column store for real-time event aggregation, and that's a mouthful, but instead, let me explain it with my cute little puppy instead. So this is Flurry. You're going to see lots of Flurry during this talk. I figured dogs were a good way to keep you awake with all of the ahs. So Flurry here is a retriever, and she likes to fetch data and ensure that people can get it analyzed for them as quickly and as efficiently as possible. So, and not just any data. It specifically is with the goal of being able to look at telemetry flowing out of your systems to help you understand what are your systems doing, WTF is going on, why is my system slow or emitting errors. And that's why you might want to look at a petabyte of data to figure out what's going on. So, hi, I'm the field CTO at Honeycomb, and I'm an AWS community hero. Funnily enough, not a serverless hero, but I do work a fair bit with serverless as well as with Graviton and ARM and so forth. And as you can tell from my accent, I'm not from here. I'm actually originally American. I live half the year in Sydney and half the year in Vancouver, British Columbia, over in Canada. So Honeycomb was designed with this premise that you could have a better experience with debugging your software applications by emitting the right data and having the capability to slice and dice it and granularly look at it without having to pre-aggregate, without having to define in advance, these are my indices, these are my dimensions, but instead to be able to ask any question and to have the system tell you what's wrong without you having to push new code to have it emit a new metric or a new log line. So with traditional monitoring, the idea was, you would have these traditional things like, hey, I want to have a metric for my number of HTTP 500s. I want to have a metric for my number of, for my CPUs in use on my MySQL database, right? And all of these things are fine, but the problem is if you ask them to do anything that you didn't anticipate in advance, like, for instance, how many HTTP 500s are being served from this specific endpoint and from this specific user agent, your metric system is not going to be able to keep up with that. So the idea that our founders had was instead, what about if we could make it so that any query was fast? And we decided that we were going to do that by kind of brute forcing the problem at read time rather than write time. So this worked up until a point where we suddenly discovered that we needed serverless functions. So here's an example of what this looks like in practice. Again, this is not meant to be a product demo. This is simply meant to be a showing you what is context in which we're operating. All right, so if I'm looking at the behavior of our custom serverless database, I might want to search for calls to invoke. And I might want to ask, let's say group it by environment ID, by the customer environment ID. So I should be able to reasonably quickly drill down and see, OK, what's going on? Which customer is contributing the most to my number of transactions? That customer looks like it's a majority of our traffic. Let's exclude that one. I'm interested in customers that don't share that property. And let's also go ahead and ask, how much is this costing us? So let's do sum of lambda cost. And let's go ahead and say, OK, how much are these customers costing us? So like we've got one customer that cost us, over the past 2 hours, $5 of lambda. Another one that cost us $3 of lambda. So the idea here is that I should be able to go in, even though I didn't explicitly define a metric for environment ID, or a metric for which call is being made, or a metric for what. Let's actually group this even further. Let's group this by query source. So let's see. Now I can have this data, not just by customer ID, but also by which subset of the UI functionality they're exercising. So you'll notice that as I was doing this, these calls literally are only taking milliseconds. I'm not sitting here and spinning and spinning and spinning and waiting for a generative AI program to output what it's doing. But instead, I'm getting these answers in real time, which is really important because if I am having an outage in my service, I really, really, really want to understand what's going on as quickly as possible. So that's kind of the core idea. And we ran into some problems when we were trying to make this scale initially. So the theory is you have a bunch of data, and you are collecting it via either kind of a proprietary protocol, or the better way to do it is OpenTelemetry, which is the third most popular Linux Foundation project after Linux and Kubernetes, and is meant to help you digest and export this data into any place that you like. I happen to think Honeycomb's a great place to do it, but there are plenty of other options out there. And then what you do with that data is then you can decompose it. You can say, I want to break this down by each of its constituent fields, so almost as if everything is being simultaneously indexed. And then you can do things like store it onto a backend data store and then query it. And what if also, because the year is 2024, what if we sprinkled some AI on it? Because why not? So emphasis, interactive, right? 100 milliseconds, like what you saw there, that's pretty snappy. 1,000 milliseconds is OK. If I start having to go and take a sip of my coffee, that's a little slow, but it's tolerable. And if I have enough time to go and get up and go make a fresh pot of coffee, that's a problem, right? That's kind of indicative that this is no better than any of the previous generations of things. So under the hood, we've got an architecture that basically consists of loads and loads and loads of Kafka, and then also writing the data out to backend storage. So originally, it used to be the case that our backend was single-homed, that you would have all of the traffic from your application going to a specific backend host, and that specific backend host would store all of the data on local SSD. Because before Honeycomb existed, our founders worked at Facebook, and Facebook had this product called Scuba, which was an in-memory query engine that was capable of doing this columnar analysis. And it turns out, if you're Facebook, you can afford a terabyte of RAM. If you're us, you can afford a terabyte of RAM. But you might be able to afford a terabyte of local SSD. So that's what we did. So we basically had the idea of, OK, if we no longer have all the data capable of fitting on a single host's NVMe drive, OK, we're going to shard it then. Let's make sure that we're sharding each incoming customer's data according to some consistent key. And then that way we know which customer's data goes on which host, and therefore which host to query, and then merge the data back together. And each host can then go and query the data on its local NVMe SSD drive. So that still kind of keeps that promise of this is fast, right? Like this is fast enough that you don't even have time to take a sip of your coffee. And then, yep, we merge it together, and we aggregate it, and that's how you kind of can make the system initially scale. And under the hood, what we're doing is we are decomposing each value. So because it turns out the data compresses really, really well, if you're storing all of your trace span names together, right, chances are there's going to be a fair bit of repetition there. Or if you're storing all of your timestamps together, chances are that those will be semi-sequential, or at least they'll share kind of the initial couple of bytes. So you can kind of get this really nice compaction. And also, if someone's querying only for a subset of the data, then you only need to read those files associated with the columns that they're requesting and not any of the other columns. So that all works pretty well, except for, what if there weren't one file per column? What if we wanted to, break it up? What if we wanted to be able to roll out old data? Let's suppose that someone doesn't need their data after 60 days anymore, right? So let's go ahead and delete older data. How do we do that? Well, you can go ahead and say, I have a bunch of files per segment. Each file contains the data for one field. And then each segment has a range of timestamps that it's responsible for. So we can say, OK, each segment is going to be no more than 1 million lines or 1 hour or 1 gigabyte of data. And we kind of have these chunks. That way we know if I get a request incoming for a certain time range, then I know that I can skip reading the segments that come before or after that time range. So the query that I just ran was only for the last 2 hours. I don't need to scan the data from 60 days ago until 2 hours and 30 minutes ago. I can only scan the data from 2 hours and 30 minutes ago that might overlap with that 2-hour time range. So we've definitely kind of continually optimized this. And now you run into the next scaling challenge. So we have a bunch of data sitting on local SSD. And sure, you can horizontally scale it, and you can horizontally scale it, and you can add more and more and more partitions. But at a certain point, you exhaust the capacity to store that data on local SSD. And we can't just continue adding more machines. And those segments wind up storing less and less and less data because we're rolling them over so consistently. And then we're eventually potentially having to age out those segments because we no longer have the space on disk, so we age out the oldest segment. And now instead of having 60 days of retention, we have maybe 3 hours of retention. That's less good. So the answer is to shove all of the data onto S3. So when you shove all of the data onto S3, that gives you a lot of really great durability promises. It gives you a lot of scalability promises, asterisk if your S3 calls don't fail. And now we can keep data for 60 days even if it doesn't fit all on local SSD. This is wonderful, except for now we've introduced another problem, which is, sure, I can go ahead and issue a query for the past 30 days of data. And now that individual host that originally tiered that data onto S3 can go fetch it back and process it and grind through it and then generate a result. But it's fundamentally limited by the fact that if that machine only has a set number of cores, maybe it has 8 cores, maybe it has 16 cores, but it definitely does not have enough cores to process 60 days of data in a reasonable time frame. So, yay, people can run queries over 60 days, but it's painfully slow. So enter AWS Lambda. Because fundamentally, like my dog, it turns out that they really, really, really want to have all the resources in the world when you're having fun and playing with them. And then at the end of the day, you have all of these toys that are sitting all over your kitchen floor because the dog is done playing with them and doesn't want them right now. So how do we deal with this kind of utilization problem, right? We could, spin up hundreds of compute workers and go fetch that data off of S3 per compute worker, but then we have to pay for that all the time. So AWS Lambda, in our case, enabled us to scale this out dynamically on demand and enabled us to achieve a concurrency not just of 100 hosts, but of tens of thousands of concurrent workers able to fetch from S3. And S3 itself is also pretty infinitely scalable as long as you've sharded your bucket well. So we were able to solve this problem of having too much data for one retriever by actually sharding out the set of data to scan off of S3 into a number of different work units that could be invoked in a Lambda invoke request. So now the increase in query time is sublinear. And if you're querying months of data, you can still get results in under 10 to 20 seconds, which is pretty good. And it turns out that you're not just buying compute in 100 millisecond units, because AWS Lambda, at least, and I believe Google Cloud does this too now, allows you to only get billed in 1 millisecond units rather than 100 millisecond units. So it means that you don't wind up paying this large fixed startup cost or this large fixed query cost. And the faster your query is complete, the less money it costs you. So this is how we were able to scale up from running things on a single host to running things across multiple hosts to suddenly running things across Amazon's broad fleet of Lambda workers and being able to get tens of thousands of concurrent workers with less than 50 to 100 milliseconds of runtime per Lambda invoke request. So this is where the site reliability engineer in me says, so there are some problems here. Let's talk through some of the problems in actually running this system. That's where that asterisk is coming from. So over the course of 2019 to 2022, we grew by a factor of 10, both in terms of the amount of data ingested as well as in terms of the number of queries that were hitting our backend. And it's only grown since then. We're now a petabyte scale data store, and we still are trying to keep to that promise of 10-second query or bust. So how did we actually do this, and how did we not make the Amazon S3 or Lambda teams cry? So first of all, let's talk about scale. So Lambda does scale within limits. You have a burst concurrency limit. You can get provision concurrency, but it doesn't quite 100% work for our model because our workload is very bursty, right? Like we're not scaling, from hundreds to thousands of concurrent Lambdas and kind of very smoothly throughout the course of a day. We are actually scaling from literally, we'll go from 0 to tens of thousands of concurrent workers running within the span of 60 seconds. And then we'll scale right back down to 0 right as soon as the user's done running the request. So if you try to exceed your concurrency limit, you'll get served a HTTP 429 saying try again, and then you'll have to requeue and try it again. And it used to be that it needed a minute of concurrent sustained load in order for your concurrency limit to raise. But the good news is, since about a year ago, it only requires 10 seconds of sustained load in order to cause an increase in your concurrency limit. So now you can actually scale by 1,000 concurrent workers per 10 seconds. But because of some clever negotiation with their AWS team, we actually have a custom concurrency model that doesn't even require us to stay sustained for 10 seconds. All things are possible with Lambda. Just talk to your account team. And this is how we actually measure and verify that we are getting the results that we expect by measuring, actually really how many invokes are running in parallel, and not just queued, but how many are actually running. So there are limits, and it's important to make sure that you're retrying requests that are getting 429s, that you are keeping an eye on whether your limits match what AWS says the limits are, and communicate with your account reps. So let's talk about another asterisk besides just, can you burst from 0 to 10,000? And let's talk about the startup time, because cold starts are a thing, right? That it wouldn't make sense economically for Amazon or Google Cloud Functions to keep everyone's runtimes hot at all times. So the median startup time is 50 milliseconds, but we see considerable variation in that. Sometimes you'll see 13 milliseconds, sometimes you'll see 2 seconds. The advice here actually is I point folks to other AWS Heroes advice here, which is the smaller you make your container images, the better. Right? That if you can make your container image only 1 megabyte rather than 100 megabytes, like that dramatically decreases the startup time because it's less data that has to be loaded from S3 into the runner. And also, the more that you share common objects with the Amazon Linux runtime or other kind of Docker containers that may already be preloaded on those hosts, the more likely it is that you'll see fast startup times. But the other cool thing about measuring when your application is both starting up cold, and then when it's running, and then when it's temporarily slept rather than shut down all the way, and then running and slept, is you can actually get an idea of what utilization are your workers concretely seeing in practice. The caveat here is that you have to make your application emit telemetry after it wakes up from sleep, right? Your application does not get to send telemetry while it is asleep, so you only get that data upon the next time that it wakes up. So this kind of gives us some idea of, okay, how many Lambdas are running or sleeping at a time versus how many Lambdas are actually currently in use out of the pool that we could conceivably be running across. And I think that this is really cool because it shows that Amazon is capable of kind of proactively pre-scaling you if their AI detects that you're about to have a spike. And they can often detect that even before we know, which is a little bit scary, but that's kind of cool to see. OK, so now let's talk about the next asterisk, which is I talked about a P90 latency. What about the other 10% of requests that don't finish within 2.5 seconds? Well, it turns out that this is the distribution of request latency. We see the vast majority finish within 5 seconds, 10 seconds, but there's that kind of band right there at 10 seconds, and then there's another band at 30 seconds. So those are caused by either Lambda choking and never actually getting around to starting up a function for that invoke request, or it's the S3 API. Because we are calling, right, like we have to, in order to fully read a segment, read all of the files in that segment. If any one of those files in that segment fails to come back, then we're sitting there for 30 seconds until we time out and are killed. But the good news is, at least in our case, I appreciated the talk earlier about how to get idempotence out of write workloads. We're a read workload here. Lambda is 100% used for read for us, so we can just retry it. So we actually use something that is called impatience. If 99% of your requests have finished, just retry the other 1%. Chances are, with the exception of that S3 outage about a couple weeks ago, if you retry the same request that was failing or stuck before, it'll succeed the next time. Basically almost guaranteed, so you just have to retry it. Other little problems, we really would like to send protobufs back and forth between our coordinators and our Lambda workers, but Lambda is really designed around API gateway and sending JSON payloads and responding to web requests. So we actually spend a considerable amount of CPU on both sides transforming JSON into proto into JSON and JSON into proto. So AWS, pretty please let us have protobuf communication with our Lambdas, please. The other fine print is if your merged time series data or other analysis comes back with more than 6 megabytes of data, you have to chunk it, or you have to store the result in a bucket and send a link back in the JSON as opposed to sending the raw result. And finally, the cost. So yes, it is true that AWS Lambda, at least per gigabyte of memory and per CPU core, is 3 to 4 times as expensive as an equivalent on EC2. But guess what? Remember that thing that I said about utilization, where it would be uneconomical for us to keep tens of thousands of EC2 instances running at any time should someone require them? So it turns out that the fact that we can get basically 100% utilization of that Lambda compute that we're paying for, and it's only 3 to 4 times as expensive as running it ourselves, I think that that's pretty phenomenal. I think that's a really great deal. The downside of this is that if you have something that goes amok, let's suppose that someone starts scraping the Honeycomb API and starts scraping, not just 7 days of data, but 30 days of data, and they're querying that data every minute, that'll start racking up a bill for us that might cost thousands of dollars. So the good news is we can set triggers on that, right? Like if you have properties like the one that I was showing you earlier of computing the number of milliseconds run and then multiplying it by the cost per millisecond, then you can actually compute the cost per customer and send an alert if saying, hey, that customer's doing something weird. Maybe they're investigating a problem and that's okay, but maybe it's something that we need to dig into more thoroughly to figure out whether there's an easier, more efficient way. But also, we can pull some levers to make things faster. And when you make some things faster on Lambda, it automatically results in cost savings, right? Because you are literally billed by the millisecond. So if you make something run 50 milliseconds faster, you're paying less money for it too. So the cool thing about the Graviton processors that Amazon launched, goodness, 3-4 years ago, is that they offer, on paper, both less cost per second that you run them, or less cost per core if it's EC2, and also they perform faster per core, which means that you kind of, in theory, can get 34% better price performance. And so we tried this with EC2 instances, and we found that we were able to get that roughly 30% to 40% cost improvement, right? That 30 to 40% price performance improvement. So when the Lambda team approached us and said, would you like to try Lambda functions running on ARM? We already were cross-compiling all of our code into the ARM architecture because we happen to use Golang, so it's easy for us to just change an environment variable and off to the races. But unfortunately, what we saw did not make us happy. Our use of Lambda was not particularly well-tuned for ARM64 out of the box in the same way that the rest of our workload was well-tuned for ARM64 out of the box. So we actually found that the P99 was about twice as bad as x86 when we first started running these trials, and that the P50 was about 30 to 40% slower on ARM than on x86. So that basically washes out all of the cost savings that you might get from that if the instances are 20% less per second. And even worse, right, like we are a business that cares about the experience of our customers. We cannot just slow down each customer's workload by a factor of 2. That's not going to make them happy. And remember, the P99 is what matters to us because we have to wait until the last result comes in, not the median result before we show a result to you. So the good news is we used feature flags. We happen to love launch directly at Honeycomb. I do have launch directly stickers in addition to Honeycomb stickers here. So having us gated by a feature flag made it super easy to swap back and forth between x86 and ARM, and even to set a percentage-based canary. And that enabled us to go ahead and say, OK, within literally 100 milliseconds of pressing the button, I managed to swap us back from 50% ARM to 1% ARM. Just enough to trickle enough traffic to be able to verify does it return correct results, but not enough to materially impact the performance of our users. So we wound up having to break out profiling in order to figure out what was going on. And it boiled down to 3 to 4 things. First of all, Amazon had launched this brand new product, right? Like they were launching, Graviton 2 had existed for a while in EC2 format, but they didn't have the capacity pool of Lambda ARM workers at the time to support our workload. So this was another case of we probably should have warned the Amazon team that we're going to start a trial with 50% of our capacity and see what happens, because they might have given us different advice on, maybe only do a 10% trial, like, we need to install more instances in the racks, because despite what they say about serverless, there are actual real servers. They do exist in the data center. Someone has to rack them. It's Amazon who does, not us, right? Like, we don't have to capacity plan them. But like your account team at Amazon will tell you that capacity planning is a joint exercise. It is not a unilateral exercise. You cannot say, I'm just going to increase my demand by a factor of 100 and expect Amazon to say, OK. So that was one problem. So we got Amazon to provision capacity, and now the capacity pool is healthy enough that basically anyone can stand up workload on demand. Again, unless you're Netflix or something. There were also a couple of other things, right? This was early in the days of ARM support for cloud native. So the Golang had changed to register calling convention for x86, but not yet for ARM. So we had to wait for one major revision of Go to support that. And also, there was a library we were using to compress the data before it went on to S3, and then we'd have to decompress it when we were reading off of S3. And that library had custom hand assembly written for x86, but not custom hand assembly written for ARM. There was a generic Go implementation for it, so it didn't break, but it was just much, much slower. So we were able to figure out what our bottlenecks were and resolve them, and then apply some profile-guided optimization to give hints to the Go compiler. And after that, we were able to go from 1% ARM to 20% ARM to 30% ARM to 80% ARM, and then we were like, oops, performance is degrading a little bit. Talk to the AWS account team, and they're like, we haven't landed enough capacity yet. OK, so we rolled it back. And now today, I can say that we're running 99% of our Lambda workload on ARM. The remaining 1% is just, again, compatibility, right? Just to make sure that if something happened and we needed to go back to x86, we could. So this is a thing that I like to show people because it demonstrates that when you deploy the right technology, right, in this case, this is the actual graph of the cost we were being charged by AWS, right? Like, this is not the number of milliseconds run. This is the cost, right? This transformed what was going to be an out-of-control graph in terms of the amount of cost that it was taking us to crunch through all this data that was stored on S3. And we were able to cut that cost by a good 30 or 40% and kind of bring it back under control until the volume of the rest of our revenue could keep up to sustain that kind of increase in traffic. So this is how we evaluate experiments like this today, right? Like, we're able to compare and contrast, what's the x86 latency, what's the ARM latency, how much is this costing, are there customers whose workload is particularly interesting with regard to variance in the performance between architectures. So in closing, my message to you is, yes, big data analytics and Lambda are 100% compatible as long as you take some basic sensible precautions. First of all, no amount of parallel Lambda compute is going to help if those Lambdas have to talk to the local SSD on one machine. So make sure that you're uploading that data from your local machine onto object storage, like S3 or Google Cloud Storage. Secondly, you need a good working mechanism to create kind of batches and to kind of create that parallelism, right? You cannot have dependencies where one work unit depends upon another. you have to be able to map and then reduce it. And you have to have the ability to invoke not just one segment file at a time, because invoking one Lambda per file is absurd, right? So you have to run hundreds or thousands of files per unit of work on each Lambda. And then, if you are running a workload that is not where a human being is waiting there for the response, maybe you don't run it on Lambda, right? It costs 3 to 4 times as much. Maybe you can afford to wait the 120 seconds to spin up an EC2 VM. Maybe it's OK for that batch workload to take an hour to run. You don't have to brute force it through as quickly as possible to return a result in less than 10 seconds. Similarly, we've had to add logic to say, even if this is on S3, if we only would have to spin up 100 Lambda workers to do this, don't even bother spinning up the 100 Lambda workers. Just run that locally. Just fetch the data from S3 onto the local coordinator. Communicate with your account team, because if you're adding a brand new bursty workload, they probably want to know about it. And profile if you are going to test switching architectures. You might find some surprises. And that's not necessarily, oh my God, Graviton is trash, right? Or x86 is trash. It's just a matter of, has this been optimized for your use case yet? So, and once you've gotten it initially running, before you scale out, use Lambda Power Tools, Lambda Power Tuner, the thing that automatically scales your CPU and RAM ratios to figure out what's the right ratio of your batch size to the amount of compute. Make sure that you are using observability layers so you can export the data from your Lambdas and get data on what's going on so that you can further optimize. And make sure that you're keeping an eye on costs, so that you do not have runaway costs that surprise you or your finance team. So ARM64 for us was a major cost and planet saver. It just required a little bit of preparation to kind of generate those build artifacts to be able to determine how much exactly we were saving and whether or not it was worth it. So nothing matters unless users and developers are happy. And in this case, that is one happy golden retriever who gets to play as much as she wants and who gets to sleep as much as she wants. So if you're interested in more about how we built this on the back end, there is a chapter of observability engineering. So we are currently, I believe, offering that book for free. If that link has expired, we can also send you a physical copy. Just send me an email, and we'll make sure to get you sent a physical copy of the book. And yeah, this is Flurry. Flurry is very happy that you came to this talk. So thank you for being here. And really, really appreciate it. And if you're interested in more sustainability stuff, I popped a link to a lead dev article that I wrote as well. Thank you so much.
Thank you, Liz.